Wasabi, you guys! Welcome to Lecture 5 of Linear Algebra for Comp-Sci majors. In this lecture, we're going to talk about vector spaces and linear combinations. Now, first of all, for vector spaces, we know what a vector space is, right? We mention it about, R of n, right? That's a big fat R of n. And then, of course, in some other countries, they use this notation as well, right? These are vector spaces. And we're going to talk more about these vector spaces. Now, I'm just to give you a little recall, right? Because we learned about determinants, and that was kind of out of the topic of what we were learning. What I mean by that is like it has nothing to do with vectors. But to recall, right, a vector v, okay, so for any vector, literally any vector that exists, okay, this is a vector where v looks like this, right? And our entries look like this, where in vector terms we say that this vector has n components, right? It has n components. This is how we spell it. Okay. So this vector has n components. Okay. Again, components, it's the same word as entries. It's like, oh, lagging. Okay. I'm lagging a lot. Okay. Stabilized. So again, components, it's a vector term of saying entries. Okay. For matrices, we say entries. For vectors, they say components. Okay. Components and entries, they're technically the same thing. It's just components is a vector word for entries. Okay. So it has n components. And then we have our vector space Rn here. Okay. Cool. So that's just to recall some vocabulary words and what it is. Now, let's consider a vector space R2. Okay, we're just going to focus on just the vector space R2. Okay, let's consider focusing in R2. Okay, or I guess to better word it, let's consider a vector space. A vector space R2. Okay? So, now you're probably thinking, so throughout the times, why do we call it a vector space? You're probably thinking, why do we call it vector space? Why are we calling it vector space if vectors and matrices are just a bunch of numbers in a box, right? Why do we call it a space? Okay, so let me show you why we use the term vector space. Okay, the truth is, the reason why we call it space is because these here, and the reason why we mathematically write it like this, right, is because we can actually convert vectors into coordinates, right? So a coordinate xy, right, from algebra, right? If you look at a graph, a 2D graph, a coordinate xy can be converted as xy. Okay? So now we have a vector xy. And you can realize that this vector fits in with a vector space R2. Yes, this vector space R2, that R2 represents a 2D graph. This is a two-dimensional space. Okay? That's why we call it a vector space. R2 represents the graph, right? If we're only talking about real, when we write like this, right? Yes, this is one-dimensional. Like, it's just real numbers. Real numbers, or literally any number. That's why when we do algebra, we write like this, this could be literally any number, because R is a number line, right? This is a number line, okay? 2, 1, 3, or negative numbers. Somewhere here there's a fraction, somewhere here there's like a square root something, right? This is a this is a one-dimensional number line. R2 is an xy plane. This is a two-dimensional space. So that's what this is. Okay? So in a vector space R2, we can use vectors, right? A coordinate, let's say, I don't know, this dot here, where xy is at, right? Then a vector, the vector looks like this. Okay? This is v. This arrow here, it's not a line, it's like an arrow pointing at this dot here, where v is equal to this vector here. Okay? This is what a vector looks like in space, in a 2D space, in a vector space, right? They're just a bunch of arrows. Okay? So those are vectors. That's what a vector look like. So an R2 is a 2D space, and the vectors are just arrows in specific directions. Okay? Vectors are directions in a vector space. Okay? Cool. So this is what an R2 vector space looks like. It's just a two-dimensional xy plane, right? And now you're probably thinking, wait a minute. Then what about, R3, R4? Then R of n means nth dimensional space. Okay? I know it sounds crazy, but there are a lot of maniacs, linear algebraic maniacs, studying high-dimensional linear algebra. We won't learn that. Definitely not, no. But there are some psychotic mathematicians who are just a little too much making love with linear algebra, doing higher dimensional spaces. Okay, let's not talk about that. Alright, so now that you know what this looks like, what does it look like when we're dealing with, vectors in a vector space of R2? For now, we're gonna focus on R2, just R2. I'm just gonna draw a 2D graph just like this for now. Okay. I'm gonna use yellow. Alright. Let's consider U, a vector U, to be AB. Okay. Again, we're just gonna focus on R2 for now, just to give you a feel of how vector spaces work. And mainly, we live in a two-dimensional, three-dimensional society. So, of course, in Comp-Sci, you're only going to work with R2, R3 vector spaces. Okay? Now, we're given, let's say, U and V, right? So what does U and V look like? So let's say, I'm just going to give an example. Like, let's just put A here. Or, will it... I just need to make sure it's not too cramped. So this is AB. So this is U. So that's our vector U. Okay? Let's say that CD is here. Okay? Then this line that is v. Okay, that's our vector v. So this arrow here is vector v. This arrow here is vector u. Okay, let me just kind of make a bigger dot so that you can see. Cool. All right. Now, what is u plus v? U plus v is equal to a plus c, b plus d. Right? So, okay. So the vector addition, this is what it equals, a plus c, b plus d. Okay. So then where is that located? Right? If a is here, right, and b, I don't know where b, oh well, b is here, right? And then, okay, so a plus c, if c is this long, right, whatever this point is, if c is, I think, let me crouch just so that you can, okay. Hopefully you can see me, but if this is the origin, hopefully you can see my hand, okay, origin here, and c is right here, right? If I move, so if the exact length of c looks like this, the size of how I'm holding my hands, try not to lag. If this is the length of c, right, from the origin, c here, and if I plus a, shift it, so a plus c is right here. Okay, so here is a plus c. Okay, so, right, and same exact thing, right? If D is right here, and B is right here, I'm sorry, D is right here, so that means that B plus D is here. Jesus Christ. I'm gonna have to draw, it's okay. It's okay. B plus D. Okay? Alright. So that means that A plus C and B plus D is equal to here. Okay? So this is A plus C, B plus D. Okay? I know it's a little crowded, but just bear with me. And so the vector of U plus V looks like this, right? Now you're probably thinking, wait, that looks random, right? This looks like randomness. Like, we know how to find, we just learned how to find a vector just by using coordinates. But let me show you what's going on behind the mechanism here, right? We call this the parallelogram law. Pretty much, we're going to take the same vector here, and we're going to land it here. So what we're doing is it's u plus v. Okay? This is the same vector as this. This is the same vector as this. This is also v. Okay? And you notice when we do u plus v, we get u plus v here, right? Again, with vector addition, right? So v here, v plus u, this is the same thing as v plus u, because, that's just how addition works. Then v plus u, this vector is u. Okay? This vector is the same thing as this vector here, u. This is u plus v. This is v plus u. They both equal to u plus v. That long vector, the diagonal vector here, this long vector, this is what u plus v looks like. This is called the parallelogram law, right? I didn't use the parallelogram, before, right? How did I find this point? How did I find this vector? I just use coordinates, right? But you can also, where this come from? Why is it here? This is how vectors work geometrically. If you add vectors like this is how, vector addition looks like. Okay? And this is, I needed to show you what this is, or what this looks like, because you can notice we can use mappings. This is how we create, track locations, whatever. We use vectors as like a map. Okay, we go this path, then we go this path, or we go this path, and then we go this path. They're both the same pathways. They, it leads to this point here. Okay, so this is what vector addition looks like geometrically in a 2D vector space. Okay, cool. All right, so now we have scalar multiplication. What does a scalar multiplication looks like? What does a scalar multiplication look like? Thankfully, I drew a bigger graph here. So let's go ahead and put in some examples. Again, let's just focus on v, right? V is equal to some coordinate x, y, right? So then v here is some coordinate here, x, y. Okay? I probably should have never drawn it like that, but, or I could just shorten it. So whenever, if we have a scalar multiplication, right? CV, some scalar multiplication, then what this means is that we are having CX, CY, right? So depending on what C is, you can either shrink the size of the arrow or expand the size of the arrow, okay? In linear algebra terms, we call it magnitude. So here, what it would look like is, let's say, let's actually make it, let's say, a scalar of 1/2 of v. Then you have 1/2 of, these coordinates. So then 1/2 of those coordinates will be here, right? So now you have a vector like that, okay? This is literally 1/2 of v. The yellow one is v. Okay? Hopefully you can see that. I hope that's not too small for you guys. Let me draw that bigger. Okay, just to let you know that this is 1/2 of v, this vector here. Okay, so all it does is it just changes the size. Right. If it was 2v, right, then it would be a lot bigger, right? If it was 2v, it would double the size. Okay? It would be located at, it will be pointing, 2v would be pointing at 2x, 2y, which is a lot bigger. Okay, but what about negatives, right? Same here. In fact, I'll do that here. With -2, -2v, right? This is equal to -2x, -2y. So now the coordinate is here, located here, x, -y, but 2 times that. So the vector will look like this, pointing downwards, the negative side. Okay? So this is what scalar multiplication looks like. It's just vectors changing It's just changing sizes. And then the negativity here just kind of reflects it and makes it point at the opposite direction. Okay? So this is how vectors work with scalar multiplication. A lot simpler looking, right? Not so bad. But this is exactly what it looks like in a two-dimensional vector space. So now let's say we're given a set of vectors. Okay, what does it look like in a two-dimensional space when we're given a set of vectors? Let me actually write it here. Let me change my position. I am too much in the middle. Let's call it W. Okay, we have a set of vectors. I'm gonna call it W for now. We used to call it S, but let me call it W for now. A set of vectors where we have a condition x plus y is equal to 1. Okay, so now we're dealing with vectors that has this type of property, x plus y equals to 1. Okay, but what does that look like in a vector space? What does this set look like in a vector space? What this means, well, it's actually very simple, right? It's literally just a graph of this. It's just a graph of that. So here, I mean, x plus y, this is y is equal to negative x plus 1. Okay, so the graph of that, it's literally just a graph of this. So negative x plus 1, that's it. This is literally what our vectors look like. So all of our coordinates land here. And so, of course, we would have like a bunch of, let me actually delete that. We don't necessarily draw it like this, where we have a bunch of vectors pointing whatever, like this. We don't necessarily draw it like that. Like we don't do that. We just leave it as is. We just leave it like this graph. Okay, this is all the points, all the coordinate points that the vectors are pointing to. Okay, and of course it's just the graph of this. Okay, so again, just to demonstrate another example, right? Let's say we're given a set, another set of vectors, right? Where that looks like an ugly. Okay, let's say like y equals to 2x. Okay, then 2x is like this. Well, let me use a blue marker. All the points. So this is all the points that vectors will be pointing at. Okay? So that's all what it looks like. That's it. Okay? And of course the vectors would just, just point to all these vectors starting from the origin. So this is what it looks like. It's literally just graphing this into a 2D plane. But this is what the set of vectors would look like when given a set of vectors like this. Okay? Right. I mean, shoot, y equals x squared, and it'll just be a parabola. But it's like, again, it's all the points that vectors will be pointing towards. So now that we learn, what it looks like in a two-dimensional vector space, R2, what about R3? Right? What about R3? Now, I don't blame you if you don't want to look at it, right? Because we all don't want to deal with three-dimensional stuff when it comes to math, but I have to show you at least what it looks like, right? So yes, when we're dealing with a vector in R3, A, B, C, or to be more accurate, X, Y, Z, we are indeed dealing with a three-dimensional space. Let me draw like this. Oh god. Okay. Three-dimensional space. Okay? And then let's say we have a point. We have some point here at, at X, Y, Z. Point here. And this vector is just pointing right there. That is our vector V. Okay? This is X, Y, Z. Okay, this is what a vector looks like in R3. It's a three-dimensional vector space. It's just an arrow in a 3D space. Okay, it looks two-dimensional, but let me bring you with me. So if you feel phantom sense or anything, I'm sorry, or for other of you guys, if you get motion sickness, I'm sorry, but I'm just gonna bring you with me. Okay. Okay. This is a three-dimensional vector space. Okay, it looks like this. I know, I'm sorry if you have motion sickness, but I'm just showing you. Okay, this is what a vector space looks like in 3 dimensions. Okay, we have here just, we have this vector space. It's just an arrow pointing at this dot direction here, just a vector arrow in a 3-dimensional space. Okay? I know it looks cool because it's a 3D marker, I know, but just want to show you what it actually looks like. Okay, enough of me showing off my 3D markers. Let me actually put you back. If I can remember, I think like that. Yeah. Okay. So yes. So that's what it looks like. I know, 3D, three-dimensional vector space. We're not gonna dive too detailed about it, because it is disgusting. I'm just gonna draw this for satisfactory. It's located here. A box. Okay. You know what? I guess I'll bring you with me again. Right. Ooh, it's so cool. Oh my god. Vector space. That does not look like a nice box, but I tried. Oh my god. Whoa. Whoa, a vector space in R3. Oh my god, so cool. To all the linear algebraists, it's just an arrow. It's just an arrow. Okay. So, pretty much in general, vectors are used a lot. I mean, I say a lot in 3D computer graphics, animations, machine learning. I don't know. I'm not a computer programmer. I know nothing about computer science fields, to be honest. But literally, just any. What happened to my arm? What the heck? That was weird. But literally anything. Machine learning. I think they use machine learning. They use vectors to describe algorithms and processes in machine learning. Defining paths and optimization. There's a lot of things. Vectors is literally everywhere when you get into like advanced computer science stuff. You will use vectors a lot. Okay, especially 3-dimensional stuff. But don't freak out. Don't freak out. I'm not gonna terrorize you with 3-dimensional drawings. Okay, so let's go ahead and do an example problem, shall we? let's say we have, let's say in Minecraft, right? I think Minecraft's a good example, right? In Minecraft, right? I don't play Minecraft to be honest, but I know there's like some corner of the screen that's like it tells you like coordinates. So let's say like player one is located in this vector here, right? We have player one located in vector like I don't know, like 10, 28, negative 15, 10, 28, negative 15, right? And then you have player two located in vector W, where it's like 30 and then 16, 27, right? So let's say you're given these vectors, and then now, of course, if these vectors are defined in 3D space, then my question to you is, I should probably label this as player one, player two, right? Player one, player two, okay. Who's mining? That's literally the question. Which player is mining? Just by looking at this vector, right? Based on these vectors, which player is mining? Player one, right? Player one is mining because z is equal to negative 15. Again, like I said, if vectors are defined as x, y, z coordinates in a 3D vector space, right? So vectors, again, they're arrows. They're kind of like they're pointing at the direction of what the coordinate is at. So if I asked you, which player is mining, of course, player one is mining because it's at below ground level. Okay. So again, that's how you could kind of imagine vectors in 3D space. This is how you can imagine vectors in 3D space. I mean, you could just think of it like Minecraft, I guess. But yeah, so that's one way of doing it. Okay. All right. Let's do another example so that we can get a clear, just to develop an intuition of three-dimensional vector space. Okay. Let's say if I'm at a coordinate, let's say I'm here right now. Okay. Let's say I'm here right now. I'm at coordinate 0, 0. All right. I'm at coordinate 0, 0, and well, the majority of you people don't play VR chat, but let's say here. Come with me. Okay. So let's say that from where I was at 0, 0, and this here, this is the dock. Okay. Now, at that beach dock there, that coordinate is 1, 1. Okay. So if that's at 1, 1, and my teaching area was at 0, 0. Okay. Now you see that place right there. Hold on. I might have to zoom in. If I can zoom in, look at that area right there. See that fountain right there? That's a fountain. Okay. Or I guess I could go a little closer. I'll just bring it to you, because why the hell not? Oh, what am I doing? Oh, I'm dumb. I have a better idea. We have a teleporter here. I forgot we have a teleporter here. Okay. Let me just teleport like this. Please do not throw up. For those who haven't played VR chat. Okay. So we have a fountain here. Okay. This is where the fountain's at. Alright. I'm just giving you a spatial awareness of where everything is. Okay. That's where I was teaching, where the blackboard is. The dock is all the way over there. This is the fountain that we were. Great. Now I have to go ahead and walk my ass to the other side. The things that I have to do for math. Okay. So, now that you get the idea of how this place is. Now, if I'm right here, where I am right now, okay? If where I am right now is 0, 0, let me make sure if I place the camera correctly. I think it was like this. hopefully. But if I'm where I'm at right now, okay, where I'm at right now is 0, 0, okay, and the dock is at 1, 1, okay, and that fountain right there, we don't know what it is, right? But we can ask, what direction or vector do I? Oh shit! Let me get something. Actually, I'll be right back. Okay. So if I have this what is the blaha? No, they call it blowhigh. If I have this blue shark, okay. Uh, whatever. Okay. Surprisingly, this where I lost my lecture note. So, okay. So to recap, right? If where I'm at right now is 0, 0, okay, and the dock is at 1, 1, and I'm ordered to, someone tells me, okay, I need you to be at the fountain. Okay, so I have this blue shark here. Okay, where, at what direction, at what coordinate do I point this? This is technically, I know it looks like a plushie, but it is secretly a weapon here. I don't know why, but it's not exactly a weapon. It's just a grappling hook. But if I need to point, right? If I need to point myself where the fountain, oh god, I almost accidentally clicked. If I need to point, if I need to go to the fountain, right, and I need to aim my grappling hook to, drive myself to the fountain, right? What direction? Pretty much I'm asking what vector do I aim my grappling hook to the fountain, right? If I am in 0, 0, that dock is 1, 1. Where is that located at, technically? So, but I want you to put your answer in vector form. So instead of a position of a coordinate, what is my direction, right? So in that case, we don't know exactly, right? We don't know exactly where it's located, right? But in vectors, with vectors, instead of knowing what exactly the coordinate is, we can aim. We can aim at the direction of a different coordinate, right? So, that fountain. What I'm saying is that fountain right there does not have to be. We don't know what coordinate it is, right? But we can say that if I'm at 0, 0, and that bridge right there is 1, 1, then we can assume that, we can say that we will aim our grappling hook. I have stick drift, so I'm trying so hard not to. My controller, hopefully my controller does not glitch and shoot me away from this place. But here, if I am aiming, I would aim my grappling hook at negative 1, 1, negative 1. I cannot speak. So if I'm at 0, 0, oh god, I'm lagging. If I'm at 0, 0, and the dock, the bridge is at 1, 1, then I would point my grappling hook at negative 1, negative 1. Right? That's not where the fountain is exactly, but it's at the same direction. Does that make sense? I'm aiming at negative 1, negative 1, right? Instead of saying the actual accurate coordinate that the fountain is located in. Okay, so I'm using vectors. It gives me the direction of where the coordinates or the other coordinates could possibly be in. So again, if I'm at 0, 0, that bridge is at 1, 1, and I need to go to the fountain, and I need to aim my grappling hook to where the fountain is. Where do I aim it to? I aim it directly at the coordinate negative 1, negative 1. Okay? Not exactly where the fountain is, but the vector negative 1, negative 1 is a direction of where I'm going to aim my grappling hook towards so that I get to the fountain. Oh my god. I'm gonna let go of this now. So let me put this in graphing form. So Jesus Christ. So if I was here, okay, and the dock was here, then the fountain is here, right? Okay, so I'm given, okay, so I know that I'm at 0, 0, or I kind of, assume that I'm at the origin, and I assume this is 1, 1, right? What coordinate is this? I don't know. I don't know what coordinate that is, okay? We don't know what this coordinate is. We don't know, okay? But that's not the point. The point is, I want to go here, okay? If I want to go here, but I don't know exactly what location that is, right? Instead of knowing what location it is, I just point my vector at it, okay? I just point my vector at it. And this point here, where my vector is actually pointing, is -1, -1, okay? Right? I don't know what it is, but I know it's at the same direction as where this point is. It's at the same direction. So just to recap, right, we don't know where this is located, but because we only focus on going where this is at, we specify our direction instead, and then we just say, okay, we need to point our direction, our vector, where this is located. So approximately, and then we use this as like to specify what direction is at. Our direction is at -1, -1, not exactly where the fountain is, but the same direction as pointing towards the fountain. Okay, so that's the usage of vectors. Okay, I know, a little complicated. I probably worded that very terribly, but a way to visualize vector space. Again, to remind you, vectors are not coordinates, they're not points, they're arrows. They are directions of a vector space. To briefly summarize, what is a vector? This is a vector, okay? It is an arrow. It is an arrow pointing at some point, okay? A vector, okay? This coordinates x, y, okay, gives direction. Gives a direction of where the vector needs to point at. Okay? Coordinates just helps us give a direction to where the vectors are pointing at. Okay. The scalar is just the size or magnitude of the vector. Okay? That's all that is. That's all that is. That's all what vectors are in a vector space. So now that we learned just a conceptual basic of what is a vector space and why we call it a vector space. Now we're going to learn a new entire topic now. Ooh, lagging. We're still dealing with vectors, but it's a different concept now, and we call it linear combination. Okay, so what is a linear combination? A linear combination is essentially just a vector. So a vector is a linear combination if it equals to this expression here. Okay? If a vector is in a form like this, in a format like this, then this vector is a linear combination of vectors v1, v2, whatever to vn. Okay? So we call this a linear combination. Okay? V is a linear combination. And the C1, C2, and CNs, those are scalars. Okay, they're just a bunch of scalars with, it could be any real number, whatever. Okay, so linear combinations are vectors that can be in a form like this. Now you're probably thinking, oh, all vectors can be in a form like that, right? That's not exactly what I mean. You will be given a set of vectors. Okay, you'll be given a set of vectors, and some vectors cannot equal with certain vectors that you'll be given. Okay, so you'll see what I mean when I give you a bunch of examples. So I'm gonna go ahead and erase that. So let's do an example. Consider 3 vectors. We have an example here, right? We have 3 vectors that were given, and we want to ask, is this vector a linear combination of those 3 vectors? Meaning, can this vector be expressed in terms of these vectors, right? Let's see. Well, so we want to see if V can actually be in a form of C1 V1 plus C2 V2 and C3 V3, right? So we could actually write this another way to just clean this out, right? We have 2, 1, 5, negative 5. This is C1, and then a vector here. You get the idea. I'm just gonna, you get the idea, right? C3, again, these are scalars. Okay, right? You can fill in the blanks. And then here, you can write it another way, right? This is the same thing as C1, C1, if you actually plug it in, right? If you plug it in, whatever, it becomes a system of equations in terms of C1, C2, and C3. In fact, this can also be in a matrix equation. Let me actually rewrite this. If I write it backwards, you get like 1 to 1, 1 to 1, negative 1, 102, negative 3. This is negative 2, right? So we can write this in a matrix equation like this, right? And then our V, 5, negative 5, right? So we want to know if this can be in a form of that, right? And we want to know, in order for this to be a linear combination of them, we need to actually have a solution, right? If we cannot have a solution, if there is no solution, if we cannot find C1, C2, C3, then we're kind of doomed. There is no, it can't be in a form of a linear combination. Okay? And so, because we can write this as matrices, matrix equations, what this means is that we can turn this simply into an augmented matrix. So let's go ahead and do that. I'm just going to save some space. Just turn this into an augmented matrix. And to find, how do we find C1, C2, and C3? We compute the RREF. And when you put that in a calculator, we end up getting, let's see, we surprisingly get something nice. Thank goodness. 1, 2, negative 1. Would you look at that? We solve our matrix equation, So it turns out that C1 is equal to 1, C2 is equal to 2, and C3 is equal to negative 1. Awesome. Cool. So now what that means is that that we do have a solution. So, I mean, it could, even if it has if it was free variables, it would still work because you have a solution. So, because of that, yes, this vector can be in a linear combination of this. And it could be literally written. Let me clean this up now. Now that we found our solution, it could literally be written as 1, which we have here, 2, and -1 here. Okay, awesome. So this vector can be in terms of these 3 vectors. That's what a linear combination means. Okay, it could be in a form of a scalar v1 plus a scalar plus v2 and so on, depending on the vectors that you're given. Okay, sometimes whenever it cannot be a linear combination of vectors that you're given is whenever you have an inconsistent or no solutions at all, then that's where you say, it cannot be a linear combination. There is no solution for C1, C2, whatever. Okay? But if you can for any solution, if you could just find a solution for C1, C2, C3, or for other scalars, then it'll work no matter what. It's a linear combination. Okay? So in this case, it is a linear combination because we did find scalars we did find solutions for the scalars. Okay? Cool. So we have another example, right? Can this vector be a linear combination of these 3 vectors, right? And how do we check? Right? We find the scalars. I'll call this A, right? Instead of using C1, C2, C3, we could just use A, B, and C, right? In this case, we have 1, 1. We have 1, 1 plus B of 1, 3. And then C, 1, -1. Okay? Equal, and we want to know, does A, B, and C exist? If they do, then it's a linear combination, and that's it. It's easy work. If they don't, there is no A, B, C, then that means that this cannot be in a form of this, meaning that 2, 8 is not a linear combination of those vectors. Okay? So how do we check this? Again, augmented matrix. We use an augmented matrix, solving for A, B, and C. 1, 3, 1, -1. Okay? 2, 8. Compute the RREF. Right? So, I mean, yeah, just, use the augmented matrix and then compute the RREF, and then you should get something like a free variable, I believe. Unfortunately, I didn't write it down. I probably forgot to write it down, but I know for sure that this is going to be having free variables. Okay, but the reason why I'm showing you this is to let you know that when you have free variables, when you compute the REF and it has free variables, it just means that there are just multiple ways. There are infinitely many solutions that this can be in terms of this, right? So because it is consistent, right? If you remember, because we do have a solution, it is a linear combination of those three vectors. And because it has free solutions and infinitely many solutions, that means that it has multiple forms. So it could be written as, oops. So this means that it can be written as 1 plus, and then a 2 of 1, 3. Okay. Plus a -1 of this vector. Okay. And it would equal to 2, 8. Okay? Right? Or we can even put in another form, right? It has another form. Right? We could put in -3, 4, and then a 1 here, and it would equal the same thing, right? So, of course, yes. So it can be expressed in terms of these three vectors. This vector is a linear combination of these three vectors, okay? Because it could be expressed in that formation with those three vectors, okay? So that's how we determine if it's a linear combination or not, right? It's okay. It could have free variables or no free variables. It could be, as long as they exist, as long as the scalars exist and that there is a solution, if there is a solution, then it's a linear combination. Okay? Let's get serious now. We have a system, like how we used to do, right? Solve the system of equations. That's it. And we write our solution in vector form. So how do we solve the system of this equation and write our solution in vector form? Okay, so if you remember, right, the good old days, recalling, we do an augmented matrix. So we make an augmented matrix. Let me put this at the top. In fact, well, actually, no, I'll leave it. I'll leave it. So 2, 0, 0, 4, right? And then we have 1, 1, 2, 1, 3, 7, -1, -1, and -2, 0, right? And then augmented line here. And then we go ahead and this is 4, 3, 7, 7. And now we write, then we compute the RREF, right? Our REF is 1, 0, 0, 0. Okay, so we have our RREF, right? We have RREF. So now we go ahead and write these in terms of each of a scalar. In this case, we notice that B here, so we're just kind of naming it, A, B, C, D, E. B and E is our free variable. Okay, so A, turns out that A is equal to negative 2B, negative 3E, plus, minus 6. B is a free variable, so that's just B. Okay. And then we have C is equal to negative E minus 2. D is equal to E plus 3. And E is equal to E. Okay. Awesome. So we have our solution here. Now, how do we write it in vector form? Okay. How do we write this in vector form? How do we write our solution in a linear combination, in a way? So, let's say, let's call our, I'll just write this vector here. A, B, C, D, E. Okay. So we have our vector here. Then based on what they equal, right? We have a free variable B. We have a free variable B. B has negative 2, 1, negative 1, 1 and 1. And then plus E, we have negative 3, 1. We have, I'm sorry, that's not 1, it's 0. There is no E in B. Negative 1. And then the rest is like 1, 1. Okay. Now we have the vector for E here. So we have a vector. We now have we have a leftover numbers, right? We have leftover numbers. Okay. And that's it. So that's all leftover numbers, right? Negative 6, 0, negative 2, 3, and 0 there, right? So this whole portion is technically our solution here, right? This is literally our solution. We write our solution in a linear combination in terms of these vectors here, okay? And so the way we write our solution, I can go ahead, let me actually just erase this. So our solution is B, and we go ahead and write it in vector form, right? This is negative 2, 1, negative 1, 1, 1. I'm going to write my matrix my vector bracket bigger. There we go. Plus e, -3, 0, 1, -1, sorry. 1, 1. Okay. I'm going to delete this now. I'm going to clean some space. Okay. So our answer is this, where B and E can be literally any number. Okay. And that is our solution. So this is our solution to the system of equations. We write our answer in a linear combination of these three vectors. Okay. And so, yeah, this is a way of writing it in vector form. Okay. Whew! Ouch, my arms. God dang. Holy hell. That was a hassle. That was a lot to write. Should have never gave myself a big system of equations. But, okay. So that's it. That's all for lecture 5. Yep, that's it for lecture 5. I know it's a lot. We learned about vector spaces and linear combinations. Hopefully this was helpful. Thank you so much for watching. Stay safe, and I'll see you.